In this video we'll be talking about the different kinds of repetition, mainly about sequences, but also about cycle repetition as well. Sequence repetition and cycle repetition are very similar in the way the context is expressed, but actually have completely different meanings. Now we will talk about some of the operators that we can use with sequences, and the first one is a cycle delay operator. So all of the examples we've seen so far when inserting a delay in a sequence have been ##1. But the 1 could be any number, including 0, which is useful, and we'll see how we can use that later. So what #n will do is wait a number of cycles before evaluating expression 2. So basically it's a way of inserting a gap where no checks are done, and that's an important thing to realise. If we look at the example S4 here, what we're saying, at every neg edge clock we're checking if not A is true. If it is, then what we will do from the next cycle, remember from the next cycle is what next cycle implication means, we have 3 cycles delay followed by B. So let's look at this on a timing diagram. At time indicated by 1, we have the enabling condition true. So from the next cycle, that means cycle 2, we check for 1, 2, 3, so we're now at cycle 4. And then on the next cycle following that, we're checking for B. Okay, so 2, 3 and 4 are the 3 cycles of delay where we're doing no checks of anything. So the assertion, given the waveforms here, will pass on cycle 5. What this allows then is differences in behaviour to be observed. So let's look at the example here, property S4. So at every neg edge clock we're checking if not A is true. And if it is, we're requiring from the next cycle we observe A. And then following that we've got a delay. But the delay is between 1 and 3 cycles, followed by B. So what we're saying with that is we don't care whether there's 1 cycle, 2 cycle or 3 cycle delay between A or B, but it has to be one of those. So we've allowed multiple possibilities for that property passing there. And we've described just what we're interested in. We're not interested in knowing whether it was 1, 2 or 3. Just any of those will do. So let's look at the waveform. Here at cycle 1 our property becomes enabled. The next cycle we must have A or the property will fail. It doesn't, so we carry on. And then we either have 1, 2 or 3 cycles followed by B. So with these arrows going up here, the signal B can rise at any of those times and the assertion will pass. So if the signal B was to rise between cycle 2 and 3 shown on this diagram, then that would mean the entire assertion would pass at cycle 3. And likewise for the other ones. However, if we reach cycle 5 and we've had no B yet, then that exceeds our maximum amount of time we are allowed to wait. So we set a maximum of 3 cycles. So if we don't observe B on cycle 5, then that will be a failure of the assertion at cycle 5. Consecutive for repetition allows us to repeat a sequence n number of consecutive times. What we've got here is on the waveform diagram is an example, and what our requirement is to check that A is never low for more than 4 cycles. How could we write this? Well, one way in which we could write this is by doing this property here, seek count. What we're doing on every neg edge clock is checking that we've got not A, followed 1 cycle later by not A, followed 1 cycle later by not A, followed 1 cycle later by not A. So that's our 4 cycles of A being low. And we're saying if we observe that, then it implies that A is true the next cycle. Okay, so that's one way of writing this. However, that's painful to do, especially if the number of repetitions isn't 4, but it was 64 instead. So what we can do instead here is say not A and put in square brackets *4, which means repeat not A 4 consecutive times. So these two properties are both equivalent, although the second one is a lot easier to write. Another important thing to understand about this is the repetition has to be a value known at elaboration time. You can't suddenly decide halfway through a simulation you'd like to change that number to something different than 4. From the code we've seen already, we might think a better way of writing this could be to use the not operator. So that will be more natural to read, more obvious what the intent was. What we could say is not, as in the literal text NOT, and then put exclamation mark A and then in square brackets we put *5 instead of *4. So what we'll be saying there is we should never observe the sequence where we have 5 consecutive not A's. The consecutive repetition can also have ranges. So what we can do, similar to the cycle delay operator that we saw before, you can say star min colon max. So what this means is the sequence will be repeated not a fixed number of times, but there is a range of times it can be repeated. How can we use this in a property? Well, we can see here that the enabling condition of the property name consec rep range 1 is A followed by not A. And just as a matter of interest, we could have also have written that as fel A instead, or $fel A. That would make the intent more obvious. So if we see the fall of A, it implies on the next cycle we have not A between 1 and 3 times followed by A. Okay, so again, this is another different way we could have written a property which checks that A is low for between 2 and 4 cycles only. So let's look at this on the timing diagram, this property here. So if we have not A at cycle 1 here, we can see from the diagram that the previous cycle A was high. So at this point here, at cycle 1, we're now enabled. From the next cycle, we have to observe not A, otherwise that's a failure. And then we're allowing A to rise on any of the next 3 cycles. Okay, so any of those arrows pointing up there, the signal A can rise at any of those times and it meets the behavior that we specified. However, if we reach cycle 5 without A being true, then that means our assertion fails at that point. If, for example, A rises at the earliest possible time it could, between cycles 2 and 3 shown on this diagram, then the property will pass at cycle 3 and then the property becomes inactive. Shown as another example here is in this property called consec rep range 2 is an equivalent property to the one we've just seen. Notice the difference in this one is that we have same cycle implication instead, and that increases the repetition ranges by 1 for each, the min and max. So one thing to be careful of and to note for this is the first of the 2 not A's that's required as a minimum is the same as the not A in the enabling condition. The second one, even though it's functionally equivalent, doesn't really convey the intention of the original requirement. There are some special and important ranges when you're defining sequence repetition or cycle delay. The lower bound can be 0. So what this means is 0 occurrences of something means it does not have to occur at all. So the sequence can be absent. So given this sequence here, A followed next cycle by B, 0 to 2 times followed next cycle by C, the shortest pattern allowed by that behavior that we expressed in the property is A followed by C, namely B's missing. So you notice also if B is 0 repetitions, then the delay to the left of it, the #1 to the left hand side after A, also disappears. The next shortest pattern that will match the behavior expressed is A followed by B once followed by C, and the only other is A followed by B followed by B followed by C. So all 3 of those kind of patterns match the behavior allowed by this sequence. The upper bound can be infinity, and we express this with a $sign. So what this says here, this sequence, is A repeated consecutively between 2 and an infinite number of times followed by B. So the shortest pattern that would match that behavior would be A followed by A, namely 2 occurrences of A consecutively, followed by B. The next shortest would be A followed by A followed by A followed by B, and the longest would be A repeating to infinity, meaning there's no requirement for B to ever occur, so the sequence may not ever end. It's an infinite length sequence. And as we discussed before, in simulation you cannot have an infinite length. There is always a finite number of cycles in a simulation. However, formal can evaluate things to infinity. Now we're going to show how the syntax is deceptively simple in SVA, because what we're going to discuss is a property that only has a few characters in it, but it can take quite a while to understand what it actually means. So this is what we talked about syntactic sugaring. It's made to look easy, and so just because there's a few characters, don't think that this is easy to understand. It's not. Consecutive repetition is easy to understand, and what we're going to talk about next is non-consecutive repetition. Its name is slightly misleading in the fact that what it means is not necessarily consecutive repetition. It doesn't mean it has to be non-consecutive. In order to express this, instead of using *n like we did for consecutive repetition, we use a single equal sign, n. What this means is that expression 1 must occur n times, but each occurrence doesn't necessarily have to follow on from one another. Let's take a look at an example again. What the behaviour we require to express is when A is high, then from the same cycle there must be 2 cycles of B before C occurs. This property here expresses that. A same cycle implication operator, B, and in square brackets equals 2, followed by C. Now, things to understand about non-consecutive repetition are that there is no restriction on the number of cycles between A occurring and the first occurrence of B. There could be any number of cycles. There's no limit on how many cycles there are between the first and second B. And furthermore, there is no limit on the number of cycles between the second B and C. So let's have a look how this works on the timing diagram here. At cycle 1 we have A occurring, so that's our enabling condition for our property. We now have a requirement for the right hand side of implication to complete. And it just so happens to be the case that B occurs that same cycle. It didn't need to. Really, it's only just so it fits on a slide. The first occurrence of B at cycle 1 may not have occurred until cycle 1,000,000,000 for all we care, and we would still be following the behaviour allowed by this property. So B's occurred once, and then some number of cycles later, it could be any number of cycles later, but it happens to be at cycle 3 on this timing diagram, B occurs for the second time. So this subterm, this B equals 2, non-consecutive repetition, that is now satisfied. And what is not intuitive is that it's satisfied until the third occurrence of B. Okay, so the term B equals 2 is true from the second occurrence of B all the way up until the third occurrence, which is why there is no limit on the number of cycles there are between the second B and C occurring. So in our case we have C occurring at some data number of cycles, cycle 5 on this diagram. This could have been cycle 20 billion for all we care. That still follows the behaviour defined in the property. Another sequence operator, go-to repetition, is expressed by a right-hand pointing arrow comprised of the 2 symbols shown. This is very similar to the non-consecutive repetition we saw on the previous slide, and the only real difference here is that because you're using go-to repetition, what it means is if you say, like, as in this property that we'll show down here, in the property whose name is go-to rep, you can see the expression of the property is exactly the same as the previous one on the previous slide. However, we have an arrow instead of the equal sign. And the difference this makes is the term here, B, right hand pointing arrow 2, ends on the second occurrence of B. It does not carry on. It's not open-ended like the previous one was. So what this property says, that if we have A, this implies from the same cycle that we have 2 occurrences of B. And just like before, there is no specification on how long we wait for the first B, how long we wait from the first B to the second B. However, and the difference between the 2 operators, go-to repetition and non-consecutive repetition, is when the second occurrence of B happens, then C must happen the next cycle, the very next cycle. So this is not an open-ended expression. The subterm B, right hand pointing arrow 2, ends on the second occurrence of B. So if we go and look at the waveform here, we see our property enabled at cycle 1. The first occurrence of B happens to be on cycle 2. It doesn't need to be. It could be any number of cycles from A. We wait any number of cycles for B to occur. The second occurrence shown on the diagram is at time 4. So what we know is at time 4, C must occur the next cycle or that property fails. Okay, and C does occur, therefore the property would pass at cycle 5. What we show now is some examples of such sequences containing the repetition operators we've discussed. We'll go over in the following 2 slides over more examples that will reinforce our understanding. So this is just really an exercise on showing you, if you see a property, then what would that mean if you wrote it down in natural language. The first one says from A there must be between 1 and 2 occurrences of B before C. Second one here says if we have D occurring, there must be between 3 and 4 occurrences of E. However, on either the third or the fourth occurrence, F must follow immediately. The upper bounds can be infinity. The lower bounds can be 0. They are the special ranges that we discussed. And what we can do is we can see from the bottom example, we can build up in relatively few characters an expression of quite complex behaviour, or behaviours should I say, because there's potentially an infinite number of behaviours that would match that pattern, and it can become difficult to understand. So we're going to talk about on the next 2 slides how we can improve our understanding of what these mean. We'll now go through a further example of non-consecutive repetition in order to reinforce our understanding. What we have here is a series of waveforms which demonstrate when properties pass and when they fail. Given the property up here, M implies we have A followed by between 1 and 2 not necessarily consecutive repetitions of B followed by C. So there is only non-consecutive repetition we've got to care about here. As we've learned, what this means is there is no limit on the number of cycles between A occurring and the first B. There's no limit on the number of cycles between the first and second B, and because it's non-consecutive repetition, there is no limit on the number of cycles between the second B and C occurring. There is no requirement for a second B either, so 1B followed by sometime later by C would also satisfy this property. So as you can see, and as we've been trying to explain throughout this lecture, the syntax is deceptively simple because there are an infinite number of behaviours allowed for that property to pass, and indeed for it to fail. So what we've got here, the first example starting at cycle 11 shown down here, is our property being enabled because M occurs. So whatever else happens, A must happen the cycle after M or the property fails immediately. Then we have one occurrence of B in cycle 13 followed by one occurrence of C in cycle 14. So what that represents is the quickest way in which the property could pass. Then at cycle 16 we have M occurring again and A on the cycle after that. So now we have a requirement for between 1 and 2 consecutive occurrences of B followed by C. It just so happens that these cycles 19 and 20 we have 2 consecutive occurrences of B. So remember, non-consecutive means not necessarily consecutive. It doesn't eliminate the possibility that they could happen consecutively. Followed at cycle 23 by C. So the property which got enabled at cycle 16 passes on cycle 23. Now at cycle 23 we also have M occurring, and you'll also notice in the following cycle both A occurs, which it has to in order that the property doesn't fail straight away. B occurs as well, but why this is here is to demonstrate that that occurrence of B is not being checked. It doesn't matter if B is present or not on that cycle. It makes no difference to whether the property passes or fails. So that doesn't count as one of the 2 potential occurrences of B. At cycle 26 we have an occurrence of B, and again at that same cycle, number 26, C occurs, but that C has no effect on that property passing or failing. We're not checking for C on that cycle. C could occur on any cycle from 27 to 31 in order to make the property pass. It just so happens that B occurs on 29. Now notice that this property fails here. The property fails at cycle 32, and the reason for this is because we have not observed C occurring. So remember this term here, B equals 1 colon 2, means between 1 and 2 not necessarily consecutive occurrences of B, and that's an open-ended expression. Now what ends that part, that subterm, is the third occurrence of B. So if we've had a third occurrence of B, it is no longer possible for that property to pass, which is why the third occurrence of B, without an intervening C occurring, causes the property to fail at cycle 32. Now we have an example of go-to repetition which uses a property which is identical, except for this time we're using the go-to repetition operator instead of the non-consecutive repetition operator. This is to highlight the difference between the two so we understand what that is. Again, the property has similar kind of characteristics as the previous one. There is no limit on the number of cycles between A and the first B. There is no limit on the number of cycles between the first and second B. That's if the second B actually does occur. It needn't occur. One repetition is enough. Now the difference is that C must occur on the cycle after the first B or the second B. Let's look at this waveform diagram to try and understand that. We start off by showing from cycle 11 M occurring, which enables the property, and then we see A, B, C occurring on consecutive cycles. That represents the fastest way in which the property can pass. Here we've got on cycle 15 we have M occurring, so A must occur the next cycle or the property will fail. It doesn't fail because A occurs. Then we have at cycle 19 B occurring, and on cycle 22 we have C occurring. Okay, so there's two things about this. We don't fail on cycle 20 because there is still possibility of C occurring the very cycle after the second B, so this is only the first B. The occurrence of C at cycle 22 has no effect on the property. Once we don't observe C on cycle 20, then what we'd do then, the way in which the property can pass, and the only way, is by a second occurrence of B followed immediately by C. At cycle 24 we have the second occurrence of B, so now it would be a failure if we didn't have C occurring the next cycle. So we know on cycle 25 whether that assertion will pass or fail. Also on cycle 25 the property becomes enabled again. Then we have an occurrence of A that has to happen the next cycle. Then cycle 28 we have B occurring. Cycle 30 we have the second occurrence of B, so now if we don't observe C on cycle 31 that means the assertion fails and it's not present, therefore it does fail. The occurrence of C at cycle 32 is too late. That property has already failed and then become inactive. In this module we've seen how sequences allow us to describe complex multi-cycle behaviour easily. We also seen how we can insert multiple delays using the #n operator, and that can also have ranges. Sequences themselves have a number of operators that we can apply to them: consecutive, non-consecutive and go-to repetition. And ranges can be defined for any of those operators in order that we can specify behaviour, not unique behaviour, but a number of behaviours which match our property requirements. That concludes our presentation, so thank you for listening. Goodbye.